Everyone. The next speaker is Nikita Gladkov.
Thank you. So I will talk about inequalities for observables. And first, I would like to talk about the setting of what's called entropy vectors. So what do we have here? So we have an underlying structure. We have random variables, x1, x2, and so on, xn, and discrete random variables, I should add. On some probability space omega. And for now, we can imagine that n is equal to 3. So we have 3 random variables on a probability space. And what we can observe, like suppose that we don't see these variables, but we can only see their entropies. So we can observe h of, well, x1 by definition, let me remind you. It's the sum over all potential values of this random variable of probability that variable takes this value times the logarithm of this probability. So we can observe it. We can also observe entropies of other variables and their mutual entropies, common total, well, entropy of them taken together. So, which means that we can kind of treat a pair of variables also as a random variable, and it can take different values, and we sum over like both values as this variable state. And we also have this entropy of all of them 3 taken together. So we have 7 observables. And we define our set gamma, which depends on this n, well, let's say gamma 3, will be the set of all possible triples these values can take. For all possible probability spaces and for all possible random variable. Okay, so this is my definition of gamma 3. And let's do an example. So suppose I have my probability space is basically z over kz for some integer z. So I have k values, and let's say x1 and x2 will be distributed independently as a uniform element of this. And let's say x3 is equal to x1 plus x2, well, mod k. So this is my setup. Let's compute just for this example. What will be the entropies? So I say that the entropy of any xi here will be by definition log k. If we have any 2 variables, they will be independent. So this is an example of 3 variables which are pairwise independent, but not mutually independent. So entropy of any 2 of them together is equal to, since they are independent, a log of k squared, because it's uniform on k squared values, or the same 2 log k. But here we have the thing. an entropy of all three of them taken together does not differ from entropy of any two of them taken together. So we also have 2 log k. So in particular, we see that in gamma 3, we have this point A, 2A, 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 I guess 2A 4 times, for A being equal to log 2k. Okay, so gamma 3 is some very specific subset of R7. Well, it has at least this point. So what can we say about the points which are there? We can say some inequalities.
Excuse me, isn't hi negative of log k? Like, I mean, isn't h of xi negative of log k?
Oh,
Oh, okay.
yes. My bad. Okay. Well, so what are some restrictions on gamma n? Well, we have Shannon's inequalities. So here is the first restriction. For any variable x, its entropy is non-negative, which is guaranteed by minus. So this thing is true. Another inequality, which is somewhat smarter, it says that something called mutual information is also non-negative. Like this thing, mutual information, is defined as a sum of individual entropies minus the pairwise entropy. So apparently this thing is also non-negative. This is something we can, well, prove from the definitions. And what is good is that the same thing is true for conditional entropies. So we can define h of x conditioned on y as, well, by like, we say that the pair, we look at values which variables x and y can take, and we take the expectation of logarithm that big X takes the value little x, so while conditioned on big Y taking Y. And apparently this is the same as mutual entropy minus entropy of Y. So this is the definition, and what is good about this definition is that it's natural, and Shannon inequalities carry on to conditional entropies. So in particular, all conditional entropies are non-negative. And if we take this definition and condition everything on variable z, it's still true. So in particular, we have, like from the first property, we have conditional entropy is non-negative. So entropy is non-decreasing in adding variables. So like entropy of x1, x2, x3 should be not less than an entropy of x1 and x2. So. Cool. So these are my Shannon inequalities. Whatever is on this board is called Shannon. Paper together, like I guess in the same paper which introduced the notion of entropy. So like they're very tensioned. Since then, new inequalities, new restrictions appeared. So probably the nicest of them is Scherer's inequality, which says that you take the entropy of our three variables, multiply it by 2, and it turns out that it's less than the sum of pairwise entropies. So this led to many wonderful corollaries, in particular in combinatorics. It's used in entropic method a lot. So this is a nice inequality, but does it give us something new in terms of which values can entropy vectors take? Turns out that no. Well, Scherer's original proof was quite complicated, and you cannot see that it's a corollary of Shannon's inequalities, but it is. Like you can do it, you can prove this only using Shannon's inequalities, breaking symmetry in crazy ways. So this is how it works. Well, so the first non-Shannon inequality appeared later, but let's focus on three variables for now. So there is a theorem by Zhang and Yu from 1997, which says that gamma 3 is actually given by Shannon inequalities. So you can basically, if you have a vector and you want to check if it's in gamma 3, you just need to check that all Shannon inequalities, which is a very finite set, are satisfied. Except for one case. Except if you have a vector which looks like this, you have, well, like in this case, you can see that a lot of Shannon's inequalities are stressed. So for any two variables, they are independent. So you have their mutual information being 0. So like this is very stressed. You have this corollary that H is not decreasing, like it's also stressed. Like you see that 2 log K, 2 log K, like it almost breaks. So when it almost breaks, you have this thing. That it can only be true if A is a logarithm of an integer. In this case, the vector is in gamma 3. If A is something else, then it's not in gamma 3. Okay, any questions about this part? So in particular, gamma 3 is not closed. Which is reasonable. Like we cannot expect compactness in a, like, I don't know, it's not even a set of all random variables. It's something big. So we are quantifying over all possible probability spaces. So yeah. Sure.
So is this reminiscent of the discreteness of the space? I mean, if you define relative entropy, for example, in the unit interval with the Lebesgue base measure, then you could also maybe get. I'm just asking if this is a reminiscent of the discreteness of the space.
I think it's not actually. I think it's not, because the way how you build points in gamma 3 very close to this point, it seems that it's a genuine effect of how the world works. So, yeah. This guys in the same paper gave the first conditional inequality for gamma 4, which is non-Shannon, but like just in a year, the same people figured out that gamma 4 and even its closure, so even if we add all the limiting points, it's not given by Shannon inequalities. So they, they have an inequality which, it has 16 terms with different integer coefficients. So you add them up, and somehow you see that, it's something that is true for all entropy vectors with 4 variables, but it's not a corollary of Shannon inequalities. And later, Matouche in 2007 figured out infinitely many linear inequalities which are satisfied by all vectors in G4, and they're all independent. And he proved that gamma 4 is actually not given by finitely many linear inequalities. It's not a polyhedral cone. Okay, so this was the development, and given that a point, given a point in a 15-dimensional space, it's not clear how to figure out whether it is in gamma 4 or not. Yes. Like the closure is convex. Yes, yes, this one is clear. We have a saving grace. Well, so the main trick in all this works was the following. So if you're given random variables A, B, and C, you can do something which is, technically B and C can be even like sets of variables. Like we use this pretty often. We can clone A with respect to B, C. So what does it mean, clone? Like we can create another variable D. So a random variable D such that together with B, we have the same distribution. And we also have this property that D is independent of a pair AC conditioned on B. So this is the property which this is the property which is called D is a clone. Like D is based on the information in B, but it's orthogonal to the information which is used by A and C. So we clone, and then the trick is we take some Shannon type inequality for clone, so we have 4 variables, and then we start cloning them in each other, cloning, and we get more variables, say 6 variables, and we take some nice Shannon type inequality for 6 variables, and then we use this properties and rewrite this inequality and then delete some terms in the clones, which we don't need anymore. And look what's left. And sometimes what's left is a non-Shannon inequality for the smaller number of variables. So take clones, write a Shannon type inequality for them. Then simplify using this. And then delete the terms which don't use the original variables. So this is basically the route which is taken to prove all the non-Shannon inequalities so far. So, okay. Any questions about the world of entropy vectors? Yes. It is a cone. Like with a little caveat like this. So here you see that it's not strictly speaking a cone, but the closure is a cone and the interior is a cone. Yes. Yes, yes, this is true for any case. This one can be proved. Yeah. Okay. Now let's go to part 2 of my talk. Okay, exactly mid-time. Let's look at connection probabilities in Bernoulli percolation. So I again have an underlying structure. And my underlying structure will be some graph with edge probabilities. So vertices, edges, and a function j from edges to r plus. And I have my Bernoulli percolation with this parameter j on g. And I also have 3 vertices, well, n vertices, a1, a2, a3, an. I just want to say for a moment that n is again equal to 3 to serve as the easiest case. So I have vertices. And what do I have? And I also don't see the underlying structure. I can only see the connection probabilities. So I can see the probability, well, in this setup, so P refers to the setup above, that A is connected to B. I can see the probability that A is connected to C. I can see the probability that B is connected to C, and I can see the probability that A, B, and C are in the same cluster. So these are my observables. And I denote by, well, so this one is for n equal to 3. You can guess how to generalize it for more. So gamma 3 would be basically the set of this, which would correspond to some underlying variables, to some underlying graph. And like there for 3, it was a subset of R7. Here it's a subset of R4. And again, a natural question to ask. Okay, I have this much board. Probably no. Should I try to use it? Yeah, let me try to use it. So let's try to build an example. So an example would be, suppose my graph is a star, PQR, and ABC. Then the probability that A is connected to B would be PQ, because we need both these edges open, and so on. So we see that in gamma 3, we have a point which is PQ, PR, QR, PQR for any PQ and R. Second 0, 1. So this is a point in R4. We can also build a triangle with probability PQR, and we get another hypersurface in R4. And if you build these hypersurfaces, you see that they are very close to each other. So if we take the unit cube in 4 dimensions and we look what is the percentage of volume between these two, we see that it's around 2% of the whole volume of the hypercube is between these surfaces. And actually, it's a property which is true for any graphs. So if you take any graph and A, B, and C, and you build the corresponding point in gamma 3, you see that this point always, for some reason, ends up being very close to stars and to triangles. So somehow, this is how the world is built. Somehow, gamma 4 takes a very small region of the space. Gamma 4 is effectively 3-dimensional with a little thickness. So there should be a lot of inequalities, but not a lot is known. So I will survey what's known. Well, the analog of Shannon inequality, like a very classical one, would be so for restrictions on gamma 3, the classical one would be a Harris-Clayton inequality, by Harris in the context of percolation, by Clayton in context of trying to solve an Erdős problem, well, actually solving it successfully. So also for FK percolation, the same inequality is known as FKG, well, the more general version. So you can just say FKG. Yes, people do it anyway. So this inequality says that increasing events correlate non-negatively. So in particular, if we take 2 events, event 1 would be A is connected to B, and the next event will be B is connected to C. These events correlate non-negatively, so we can have that their product of their probability is less than the probability that A, B, and C are in the same cluster. So as you see here, the inequalities stop being linear. The inequalities we have in this setup, they tend to be polynomial, but I think it's also just a feature that we cannot prove much. Probably there are some smart inequalities with crazier functions. So we'll see. But this is a nice inequality. Actually, we can say more. Instead of taking this event, B is connected to C, we can take another event which is increasing in edges. We can take the event that either A is connected to C or B is connected to C. This event is also non-decreasing, but the intersection of these 2 events will be exactly the same. So ta-da, we got a better inequality. And basically, this is all what was known for like 40 years about gamma 3. So this is it. This is the set of inequalities. Well, there are other beautiful inequalities for gamma 4, for example. So for gamma 4, we can say that from the work of Vandenberg-Kasten, so it's usually called BK inequality. You can say the following thing. You can say that if you have a probability, if you have an event that 4 vertices are in the same cluster, you can draw the picture A, B, like you will have some tree connecting them because they are in the same cluster. And in this tree, you will have, like, this is how the trees work. You will inevitably have 2 non-intersecting pairs between pairs of vertices which have paths between them which do not intersect. So you can say that the probability here will be less than the probability that 2 of the vertices are in the same cluster squared, because we have two disjoint witnesses for these events. So this is an inequality which, for example, prohibits the strange state. So we cannot have the situation when like the probability that any 2 vertices are in the same cluster is approximately 1/2, and the probability that all 3 of them are in one cluster it's also approximately 1/2. So like this situation is not inside gamma 4, like this idea. So this case was observed by Tom Hodgecroft. It's a partial. Yeah, it's a special case of his universal tightness theorem. So for 4 vertices, we cannot have like all of them separate or all of them together. So you should have some decent sized middle ground. And the same is true if we take more vertices and more observables. So BK inequality gives you some time. Okay. So let's talk about new restrictions, which we can do, and what is the main trick to get them. Well, let me first tell you the main trick. So the main trick would be as follows. So if you have 2 percolation configurations on graph G, C1, C2, you can build other Bernoulli configurations on the same graph using exploration. So you can explore the cluster of some vertex in C1, say that you add it to your new configuration. You can explore then some part of C2 and decide to not add it to your configuration. And if you do it like this, the configurations which you will obtain will be also Bernoulli, and they will have some strange dependencies. So you start with 2 configurations, you build like 3 other configurations, which will have some combinatorial things. Like if in this configuration A is connected to B, and in this configuration B is connected to C, then in this configuration A is connected to C, something like this. So you do it via exploration, and then you can exploit their dependencies. And also optionally apply Harris-Plateman and BK inequality here as well. So this main trick gives you, okay, while we're at it, remember the visual part of shear's inequality because I'm erasing it, and I will have an inequality which looks like this. Okay. So we have the following inequalities. One nice inequality, which I can give you, is that the probability that 3 vertices are in the same cluster times the probability that 3 vertices are in 3 different clusters is actually greater or equal than, sorry, I will write it as E2 to fit it on the board. Like by this, I mean a sum of pairwise products. So we have the probability that A and B are in the same cluster, but not C. We have the probability that A and C are in the same cluster, but not B. And we have the probability that B and C are in the same cluster, but not A. And I take their pairwise products, and it turns out that sum of 3 pairwise products is dominated by this product. So and this is actually strictly stronger. Like if we have here 3 pairwise products. If we delete any of them and leave 2, we will get basically this inequality here. So if you delete any term from here, you get the inequality on the right side. So it's like a way to make it symmetric and make it stronger. Like because for this Harris-Clayton inequality, you can see that A, B, and C are not symmetric. This is. So life is good with this. So exploration helps us to uncover new, like non-Shannon inequalities. Also, we can build an analog of universal tightness here with Alexander Zemin from MIT. We can say that the same thing, or here we can even break the symmetry and say that we don't require A and C to be disjoint, like it will still work. And we can estimate it from below. We say that this product is actually less than the sum of 3 probabilities less than the probability that 2 vertices are in the same cluster and the 3rd vertex is not in the same cluster. So this is also done via exploration. And you can also see it as a kind of universal tightness. This one prohibits you to have a blinking situation, to have the situation when like sometimes they're all together, all in the same cluster. Sometimes 3 vertices are all in 3 different clusters. And almost never you have the situation when 3 of them like split as 1 by 2. So like exploration helps you to build something stronger than BK in some cases. I know, it's beautiful. So it's like a stronger universal tightness. Does this imply this? I don't know. I never checked. Like it might very well do. I would say like what I have checked is that this one implies that let's try to find the maximal P such that with probability P they can be all in the same cluster, and with probability P they can be all in different clusters, let's say ABC. Like this one implies the bound of 38% on P. And here for 4 vertices, this one implies a bound of 37% on P, something like this. But like here, it's a different P, it's a P for 3 variables. So yeah, but general, like you can reprove most of the BK stuff just by doing exploration. Like it will be just exploration on the graph where G also plays a role. Yeah. Okay, and another inequality would be a very Shannon-like inequality. So a Shannon-like inequality would be the following. Like there you had twice the entropy of 3 variables. I take, well, a connection probability of 3 vertices squared, and I claim that it will be greater or equal than 8 times the product of pairwise connection probabilities, 2-point functions. So, well, this 8 is kind of unfortunate. Well, at least this can be applied to small probabilities. Like if we know that 2-point function decays like power p, then we know that this thing decays as a power p to the 3 half. So. I'm always bad with my sides. Side inequalities. Yes, yeah, okay, this is how I remember. Yes. It's unfortunate, yeah, so 8 is a big number, so whichever side contains 8 is big. Yes. Okay, so this is like a shear type. Well, actually, similar things happen with Kolmogorov complexity. If you have strings A, B, C, you can define their mutual Kolmogorov complexity. And it turns out that if you have an inequality for entropy vectors, you have a corresponding inequality for Kolmogorov complexities, also up to some ugly, well, additive constants, but yeah, additive logarithms, I guess. So my hope for big picture would be that something like this is true, and you can bring some inequalities from entropy. You can get some wonderful inequalities with logarithms and solve some wonderful problems. Like we have Gadi in this room who conjectured the correlation inequality, which is a restriction on gamma n, which would imply theta pc equals 0 for Bernoulli percolation on ZD, which would be a huge prize. Coming from a correlation inequality, and I don't know, and we are kind of bad in proving correlation inequalities. This is my point. So it's pretty plausible that there are some parts where correlation inequalities are. And let me finish with my favorite open problem. So, well, second favorite after Gadi's open problem, of course. But so open thing. So we know that we have this inequality, Harris-Clayton inequality for 3 vertices, and the equality case would be where B separates A and C in the graph. So this one has the same equality case as the stupid inequality. We say that if three vertices are connected, then A and C are connected. And also the equality case is when every path from A to B goes, from A to C goes through B. So let's denote this inequality by 1 and this inequality by 2. So since they have the same equality case, maybe we can subtract one from another until it kind of, until you cannot subtract it anymore. The question is like, can you find like something like this? So this question is usually called stability of inequalities. So the question is, do we have some stability here? Can we find a function f from r plus to r plus? So some non-negative function f such that we take the first one, subtract the second one, subtract some positive function of the second one, and we still get something non-negative. Okay, so this would be a wonderful problem to solve. And yeah, thank you.
Are there any questions?
I guess this works. So about these missing points from gamma 3 in the entropy case, suppose that I look at the set of measures, probability measures on R3, like there's a map from here to gamma 3, which is surjective, I guess.
Mm-hmm.
If I take a sequence in the image converging to one of these missing points, is there anything known about the behavior of the measures on R3? Like what sort of behavior do they do? I guess they can't converge to measures, so what happened?
So these things are defined on different probability spaces. So you have a probability space with 10 points, 20 points, 30 points, and like you have a measure here, measure here, measure here, measure here. And
if I push all of those forward to R3, right? If I only have 3 random variables and there is some measure on R3, which is just the image measure of this thing. So I certainly for gamma 3, I can collect everything in the class of measures on R3.
Measures on R3, like
the joint distribution of your 3 random variables.
Yes. I don't see why it's on R3. I always think it's some discrete set. No.
For gamma 3, I look at all possible triples of random variables, right? For any such triple, no matter what the background space is, I can push the measure on my background space forward to a measure in the image. That's on R3. So I get a measure on R3. It's a discrete measure on R3.
Okay, discrete measure on R3.
Not bother me. I'm just curious, like, because if I look, right, so look at a sequence of measures such that the corresponding entropies converge to a point which doesn't, like, it's not compatible with being an entropy.
Mm-hmm.
What happens to my original measures? But if this, it's okay. If this is.
Yeah, I'm not sure. Yeah, I'm really not sure, like, how this construction would be. Like, I would say the thing which we don't have for measures is well, for discrete random variables is compactness. Like I wanted to initially have like 3 parts instead of 2. Like also to have a third part where I would tell about the symmetric functions, because like the science underlying them is beautiful, and you have a wonderful theorem by Sturm from 1829, which is, I don't know, which I discovered not so far ago and fell in love with it. So if you have underlying things, you have some numbers x1, x2, x3, which are greater than 0, and you can only observe they're symmetric things, E1, E2, E3. Like in this case, you get closedness of all the possible values of this thing in R3 by compactness, by saying that like you take triples of non-negative numbers and like a convergence sequence converges here just now. Also, like what helps is that the function which maps three things to their values to their symmetric polynomials is continuous. Like here for entropy vectors, I'm not sure you have some I'm not sure you have compactness, and I'm not sure you have continuity. Like I'm not sure you have topology on random variables where you say that if you change your random variable a bit, the entropy changes a bit. So, like you can always like for total variation distance, for example, you can modify your random variable a bit, and the entropy will be just infinite. Like,
sure. Great, thank you.
Hello. Yeah. No, I have a question. So could you say a few words on the proofs? I mean, the type of exploration you use or something like this?
Sure. So the main exploration argument we use has the following form. So you look at the configuration C1. So some edges are open, some edges are closed. You look at the configuration C2, and you do the following thing. You reveal each edge in both C1 and C2, and before you reveal, you pre-commit whether you will take, and you're building the third configuration, let's say C3. Before revealing the edge, you pre-commit whether you will take it from C1 or from C2. So like on step one, you say, okay, I'm gonna take this edge and to reveal this edge, and I pre-commit that I will take it from C1. So you do it, you reveal this edge, and yes, it's closed here, it's closed here. And so it will be closed here. After you make this decision, you're free, like you may run a decision tree, like which does like based on what was revealed. You say, okay, the next edge I reveal will be this one, and I pre-commit that I will take it, takes the state of this edge from C2. And you look here, reveal, it's closed here, open here, but you pre-committed to C2, so you take it open. So if you pre-commit on a stage, if you run decision tree, reveal edges according to the decisions, and pre-commit before taking an edge, whether you will take it from C1 to C2, the configuration which you will get will be distributed as Bernoulli percolation. And then you have some combinatorics. You can, for some decision trees, you have like, if in C1, these two vertices are disconnected, and C2, these two vertices are disconnected, here, all three of them will be. Like you have some combinatorial things like this. But the main laminate is decision tree.
Other questions? Okay, let's thank Nikita again.